If I hold a coffee cup a certain height above the floor, this cup has gravitational potential energy. In other words, some amount of stored energy due to its mass, the gravitational acceleration or free fall acceleration, and the height above the ground. Now, if I want to transform this energy into kinetic energy, I can drop the cup. And as the cup falls, it uses this stored energy and converts it into movement energy or kinetic energy. But when we transform energy like this, we're constrained by a fundamental principle, and that is the conservation of energy principle. And this principle tells us that energy can neither be created nor destroyed. Or we can also say this as the total energy in an isolated system remains constant. Okay, let's break this down to make it a bit clearer. Let's look at the motion of a pendulum as it swings from side to side. Now we're going to treat this pendulum as an isolated system, which means that it does not interact with the outside world. The only energy in this system will be the gravitational potential energy and the kinetic energy of the pendulum itself. Now in reality, this can never truly be an isolated system because some of the pendulum's kinetic energy as it swings down, as it swings backwards and forwards, will be spent pushing the gas molecules out of the way and overcoming friction in this pivot here. But if it could be an isolated system, this pendulum would swing forever because the total energy in this system will never change. It will never leak away. Because we're dealing with only kinetic energy and potential energy in our isolated system, we can refer to the total energy in this system as mechanical energy. And mechanical energy is the sum of the kinetic energy and all forms of potential energy in the system. Now with this pendulum, we've only got one form of potential energy, and that's the gravitational potential energy stored in the pendulum as it's raised above this minimum height here. But the equation for mechanical energy is mechanical energy is equal to the kinetic energy within the system plus the sum of all the potential energy in the system. So in our pendulum situation here, our mechanical energy can be written as the kinetic energy plus the gravitational potential energy. But let's say we have a different type of pendulum that is also in an isolated system. Now this pendulum comprises of a weight on a spring, and this weight moves up and down. So here we're not only interested in the kinetic energy of this pendulum and its gravitational potential energy, which is the stored energy due to the height above its minimum point, but we're also interested in the elastic potential energy from the spring. And this will also contribute to the total energy of the system, the mechanical energy. So in this case, the mechanical energy will equal the kinetic energy in the system plus the gravitational potential energy plus the elastic potential energy. In other words, the stored energy in the spring. And it's important to remember that mechanical energy is not a unique form of energy like kinetic energy or nuclear energy or chemical energy and so on. Mechanical energy is simply the sum total of all the kinetic energy and potential energy within an isolated system. In an isolated system like these two examples here, mechanical energy is conserved, which means the total energy doesn't change over time. So if you were to set these pendulums in motion and introduce mechanical energy into the system, then these pendulums would swing forever. But the kinetic energy and the potential energy does vary over time. It's just that the sum total of their energies remains constant. And let me show you how these vary. So when our pendulum has swung fully up to the left here and momentarily stops moving, in that fraction of a second, its average velocity is 0. When this velocity term is 0, the kinetic energy is 0. But remember, the mechanical energy remains constant. So if this kinetic energy term is 0, in this situation, this must mean that the mechanical energy is equal to 0 joules for the kinetic energy plus the gravitational potential energy. So the gravitational potential energy is at its maximum when the pendulum is at its highest possible point. But this won't stay like this for very long. As the pendulum swings downwards, this gravitational potential energy slowly gets converted into kinetic energy again. And we know this because as the pendulum reaches this point here, this lowest point, the pendulum is moving at its maximum speed, which means we've got our maximum kinetic energy here. But this is the lowest point our pendulum can be in this system. And remember, the gravitational potential energy is equal to the mass of the pendulum times the acceleration due to gravity times the height of the pendulum. And if this height is 0 here, because the pendulum cannot possibly get any lower than this, then this 0 term would mean that the potential energy is 0. So at this situation, the mechanical energy is still constant in the system, it's above 0. Our kinetic energy is at its maximum point, but the potential energy is 0. The energy has only transformed into a different form. So in the absence of friction and air drag, the total mechanical energy remains constant. And we call this the conservation of mechanical energy, where the initial mechanical energy is equal to the final mechanical energy of the system. So let's imagine when our pendulum is up here or up here, this is our initial state. And this makes sense because if we want to get our pendulum moving, we're going to need to lift our mass up to this point here and then release the mass. So this is our initial state. And this is where we have our maximum gravitational potential energy. When we release the pendulum and it arrives at this state here, it has its maximum kinetic energy, and that's our final state of the system. So we can expand out this formula like so. Because the mechanical energy is the sum of the kinetic energy and all the potential energies of the system, our initial mechanical energy is equal to the initial kinetic energy plus the initial gravitational potential energy. And that's equal to our final mechanical energy, which is equal to our final kinetic energy plus our final gravitational potential energy. So let's try a few example questions now. So the first question says, if a pendulum's mass is released from a certain height such that the speed at the lowest point of the swing is 0.5 meters per second, what is the initial height from which the mass was released? And no friction is present in this system. So because no friction is present, this means it's an isolated system and mechanical energy is conserved. So the initial mechanical energy is equal to the final mechanical energy in this system. And because the mechanical energy is equal to the sum of the kinetic energy and all the potential energies in the system, we can write this equation like so. So the initial kinetic energy of the system, so the kinetic energy when this mass is up here or up here, plus the initial gravitational potential energy, which is equal to the mass multiplied by the acceleration due to gravity multiplied by the height above this lowest point here. So that's our height. This is equal to our final mechanical energy, which is equal to half times the mass times the final velocity squared, and this is the velocity of the mass when it's down here, and this is our final position, plus the gravitational potential energy when this pendulum is in this final position. Mass times g times the height, and the height here is 0. We've set this height at the bottom here to be 0. Now our goal is to find out what this height is. Well, we know the instant we let this pendulum go in this state, the velocity is 0. It doesn't yet have a velocity. So this initial term, this initial kinetic energy, is 0 joules. But it does have a gravitational potential energy because it's been lifted above the 0 point here. So plus the mass of the bob times g times some heights that we don't know yet. We know that at the bottom of the swing, the pendulum is at 0.5 meters per second. So we know this velocity here, the final velocity. We don't know the mass of the bob, but that doesn't matter yet. So half times the mass times its velocity, 0.50 meters per second squared. Now at this lowest point, the gravitational potential energy is 0 because the height, this h term, is 0. So we've got 0 joules there. So all we need to do in order to get this height term is rearrange this equation to make the height the subject of the formula. Now we've got mass on both sides of the equation, 1 power of mass on both sides, so this can be cancelled out. The mass doesn't matter here. Now we can divide both sides of the equation by acceleration due to gravity to get rid of this g on this side of the equation. So this means that our final equation, the height, is equal to the velocity squared, 0.50 meters per second, all squared, divided by 2, divided by acceleration due to gravity. So if you plug this into a calculator, we get a value of 0.013 meters to 2 significant figures. Now our second problem is a bit more complex. A spring is positioned vertically and compressed by a downward force, causing it to be pushed down by 5 centimeters from its natural length. A ball bearing with a mass of 25 grams is placed on top of the spring. If the spring constant is 50 newtons per meter and the spring only extends vertically, what will be the speed of the ball bearing when the spring returns to its natural length? So let's draw out the initial and final state here of our spring. So the initial state is when our spring has been compressed down by 5 centimeters from its natural height, which would be up here. The final state, when we remove the force on the spring will move back to its initial height. and release its elastic potential energy and impart kinetic energy to this ball bearing here. Now again, we're going to assume no friction is present and only two types of energy are operating here: kinetic energy and potential energy. This means that the mechanical energy in this system is conserved. But we're also dealing with two forms of potential energy here. A spring can store energy through elastic potential energy, but the spring and the ball also change height, which means the ball gains gravitational potential energy from its initial state to its final state because it's increased its height. So how can we write this out with our mechanical energy equation? So our initial mechanical energy, we know that our initial kinetic energy here is 0. So our initial mechanical energy, we've got an initial kinetic energy term. We've also got a compressed spring, so we've got an elastic potential energy term. And because we're dealing with height here, a change in height, we also need to look at gravitational potential energy. And in our final state, we've got a kinetic energy term, our final kinetic energy. We've got our final elastic potential energy in the spring. And we've got our final gravitational potential energy in the ball bearing. So in our initial state, our ball bearing is not moving. It's got 0 velocity. So our kinetic energy term here is 0 joules. We do have an elastic potential energy here because we've stored energy in the spring as we've compressed it. And if you have a look back in my previous lesson on potential energy, which you can view up in the card here, you know that the elastic potential energy for a spring is equal to half times the spring constant times the distance the spring has been compressed squared. The gravitational potential energy for this initial state is 0, simply because we've set our height here to be 0. Remember, gravitational potential energy is mass times g times height. When height is 0, the whole term here equals 0. Now this equals to our final kinetic energy, and we know intuitively when we release the spring, this ball is going to have some velocity. We don't know what this velocity is yet, but we know the mass of the ball. So half times 25 grams multiplied by the final velocity squared. Now, when the spring is at its relaxed length, it no longer has any elastic potential energy. It doesn't have any stored energy in its spring. But we do have gravitational potential energy here because the ball bearing has moved up by 5 centimeters. And I'm just going to write this out without the values here just to make it a bit clearer. And we're going to add in these values shortly. So half times mass times velocity squared, we've got 0 elastic potential energy plus we have gravitational potential energy, which is mass times the acceleration due to gravity multiplied by the height, the final height. So what do we do with this equation here? Well, our goal is to find out the velocity term here. We know the mass of the ball bearing, we know the acceleration due to gravity, we know the height that the ball bearing has risen by when the spring has returned to its relaxed length. We know the spring constant at 50 newtons per meter. We know the distance that the spring was compressed, which was 5 centimeters. So we have all these values here except for the velocity. So we can rearrange this to make velocity the subject of the formula. So let's do that. So I'm going to move this kinetic energy term over to this side. So half times mass times velocity squared is equal to the elastic potential energy in the spring, half times the spring constant times the compression on the spring squared, minus this term here, the gravitational potential energy, simply because we need to minus this term from both sides of the equation. So minus mass times g times height final. I'm going to multiply both sides of the equation by 2 to get rid of this half term. So mass times velocity squared is equal to the spring constant times the amount the spring was compressed squared, minus 2 mgh. We're going to divide both sides by the mass of the ball bearing, velocity of the ball bearing squared, the final velocity, is equal to the spring constant x squared divided by m minus 2gh, because m has been cancelled here. The last thing we need to do is get rid of this squared term, so we square root both sides. So the velocity, final velocity of the ball bearing as it's being launched into the air, is equal to the square root of the spring constant times the distance it was compressed divided by the ball bearing's mass minus 2 times the acceleration due to gravity times the height that the ball bearing has raised from its initial position. We're going to put some values into this now. Our final velocity is equal to the square root of the spring constant, which is 50 newtons per meter, 50.0 newtons per meter, multiplied by the distance that the spring was compressed, and we're going to say it's negative 0.05 meters squared, and it's negative because we're pushing it down. We're going to divide by the ball bearing's mass, which is 0.025 kilograms, 0. And we're going to minus this by 2. We're going to multiply this by 2 times the acceleration due to gravity, 9.81 meters per second squared, multiplied by the height above the 0 level, which is 0.05 meters. So after plugging this into our calculator, we find that the final velocity of the ball bearing is 2.00 meters per second to 3 significant figures. Now notice here that not all of the spring's elastic potential energy was converted into kinetic energy. Some of that energy was converted into gravitational potential energy as the ball gained height. Now if we laid this spring on its side in a horizontal position and no friction is present, do you think the ball's final velocity would be higher than 2 meters per second, lower, or the same as this example here? So if our ball bearing was positioned like this and the spring was like this, and there's no friction, and the ball from its initial position to its final position doesn't gain any height, well, the velocity of this ball bearing in this example should be higher because all of the spring's elastic potential energy is being converted into kinetic energy, and none of the total mechanical energy of the system, and remember mechanical energy is conserved here, which means that it doesn't change, none of this total mechanical energy is being converted into any other form of energy. For example, gravitational potential energy here. All of it is being converted into kinetic energy. So our velocity for this ball bearing, for the same spring and the same compression, will be higher if it's laid down on its side than if it's launched vertically upward.